Alright, welcome back to Mathematics Lifeline. In today's video, we're going to do 10 integrals that progressively get harder. This is actually a part 2. In the first video that I did on this, it was pretty easy integrals, and a lot of the comments were even saying they were pretty easy. So I thought I'd do a part 2, kind of ramp it up just a little bit. It's still not too complex, and students who have gone through Calc 3 should be able to understand these integrals. At least understand once the explanation is presented. So yeah, go ahead and try all these out before I start, and then of course I'll do the solution on the board. So we'll go ahead and start with number 1, and some of you, most of you actually, would probably be able to have solved this before we even started. Right? This is just a power rule. So when we do the power rule for integration, we just add 1 to the power. So we're going to have 3x to the third power, because we add 1 to the 2, and then we divide by that same power, right? Divided by 3, and then you don't forget your plus c. And then the only other thing that we can do is we have a 3 in the numerator and denominator that can cancel. So our answer is going to be x cubed plus c. And that is as easy as the first one gets. So hopefully you're able to do that one, and we'll go ahead and move on to integral number 2. All right, so here's the second integral. So this is the integral of negative cosecant squared of 4x dx. So this one may look a little bit ugly, but there's really nothing that's too advanced here. This is really just a u substitution. So we're going to say that u is equal to 4x, right? Because that's the input of our function here, and it's not just an x. So we need to make it a 4, or we need to change that into a u in terms of just one variable. So we have u is equal to 4x, which means we need our du for our u sub, which is just the derivative of u. So the derivative of u is just going to be 4, and then we'll add that dx in there. Now we don't have a 4 dx, so let's just go ahead and try to substitute dx. So we'll divide by 4 on both sides, and we get that 1/4 du is equal to just dx, right? Because these 4's will cancel. So essentially, when we make our u substitution, we need an extra factor of 1/4 to come out to the front. So we'll pull that out here. And then we have the integral of negative cosecant squared of, instead of 4x, we've substituted it to be u. And then remember, the dx will be replaced with 1/4 du. We have the 1/4, so all we need is just the du. Again, it may still look a little bit ugly, but the nice thing about negative cosecant squared is that it is the derivative of a basic trig function, right? The derivative of cotangent is negative cosecant squared. So the integral of negative cosecant squared will just default back to that cotangent value. So we get 1/4 cotangent of u plus c, but that's not our final answer because remember u was 4x. So we end up with, I'll write it like this, cotangent of 4x over 4 plus that constant c. So that's the answer to our second integral. We'll go ahead and move on to the third one. All right, so here's our third integral. So we have the integral from 1 to infinity of 17 over x squared. So this is actually our first definite integral. So we'll go ahead and evaluate this in the same way. Now, this is technically an improper integral because we have that infinity as a bound of integration. So in theory, we need a limit there. So what we're going to do is we're going to set this up as a limit. So let's say that we have the limit, we'll use a as the variable, as a goes to infinity, of the integral from 1 to a of 17 over x squared dx. Now again, a lot of people like to kind of leave that limit out, but technically it is a limit, so we're going to add it in this, at least for this question. We'll use it later and we won't even worry about adding that limit. But now what we need to do is evaluate this integral like normal. So this is, again, just going to be a power rule, right? Because I can rewrite this, let me write it all down. I can rewrite this entire thing as 17x to the minus 2 dx, right? This is the same thing using our rules of negative exponents. So then we can just use the power rule. We need to add 1 to the exponent and then divide by the same thing. So we're going to have the limit as a goes to infinity of, when I do this, we're going to have 17x to the minus 1 over negative 1, right? And I'm evaluating that from 1 to a, but that's the same thing as the limit as a goes to infinity. This is a negative 17 over x. So negative 17 over x evaluated from 1 to a. So now I need to evaluate the integral like normal, and then we'll take the limit at the very end. So I have the limit as a goes to infinity of. So I'll have negative 17 over a to start, and then I'll subtract off, but I'm really adding because I have this negative right here. So plus 17 over 1. Now, of course, 17 over 1 is just 17. And now this limit, as a goes to infinity, well, the denominator is getting really, really big, so the entire fraction is getting really, really small. So this is going to, of course, be 0 plus 17, which evaluates to just 17. So that means that our answer for this definite integral is 17. So that's it for number 3. Let's go ahead and move on to number 4. All right, so here is our 4th integral. So this is where I said you may need to even be into Calc 3 to do some of these. This is just a double integral. Now, it's not a hard double integral by any means. I think a lot of students would actually be able to understand it. But if you wanted to do this one on your own, you may have needed to see double integrals before. But essentially, the trick here is we need to evaluate the inside integral first. So this integral of 4xy dx, we need to evaluate that to start. So we're going to treat it like a normal integral. The only difference is that we're taking the integral with respect to x, so y is treated as a constant. So the whole thing, we have the integral from 0 to 1. When we do the integral on the inside, remember x is our variable and y is the constant. So we're going to end up with 4x squared y over 2. Again, this is just the power rule here with x, right? Think about the integral of 4x. It's going to be 4x squared over 2. But the y comes along because it's just a constant. And then we're evaluating that from 0 to 1. And then this big integral is still a dy. Right, so we're going to go ahead and rewrite this as the integral from 0 to 1. This will simplify to 2x squared y. Evaluate that from 0 to 1, and then we have dy. Now, again, we're plugging in 1 and 0, but we're just plugging in for x. So if I plug in 1, I'm going to just get 2 times 1 squared times y. So that's just going to give me a 2y. And then if I plug in 0, well, everything's going to go to 0 because I'm just multiplying by a 0 term. So the only thing I have from evaluating this is a 2y. I still have the dy left over from the big integral, and now we do the outside integral, now that we've evaluated everything on the inside. But again, this is just a power rule. It's really not too bad. So we just have that this is the same thing as 2y squared over 2. Evaluated that from 0 to 1. But 2y squared over 2 is just y squared from 0 to 1. And if I plug in 1, I get 1. If I plug in 0, I get 0. So if we subtract 0, nothing changes. So our answer here is 1. So yeah, not a difficult double integral, but a double integral nonetheless. That's why it's even ranked number 4, right? This could be 1 or 2 for Calc 3 students. But yeah, so that's the end of integral number 4. We're going to go ahead and move on to integral number 5. All right, so here's our 5th integral. So this is the integral of 4 times the natural log of x. Now, if you've seen this integral before, you know it's not too hard. The difficult part is knowing the trick. If you don't know how to start this one, you may be stuck for a little while. The trick here is actually integration by parts. And it looks weird because it looks like we really only have one function, but remember that the dx is technically eligible to be used, right? We can use it as 1 times dx. So we're going to treat 4ln x as our u, and our dx is just going to be our dv, right? So I have that u is equal to 4ln of x, which means that du is going to be equal to 4 over x dx. And then I have dv, which I'm saying is just dx. So the integral of dx is just going to be x. So when I get v, I'm going to get x. So that's the trick there. And then now I set this up using my normal integration by parts formula. So I have uv, which is going to be 4x times the natural log of x, minus the integral of v du, right? But v times du is just going to cancel those x's out, and I just get 4 dx. And integrating 4 is about as easy as it can possibly get. That might be level 0 of this. We'll get 4x ln of x minus the integral of 4 is just going to be 4x, and we'll add that plus c at the end. So again, not a difficult integral. If you've seen the integral of ln x, this is exactly the same process, just with that factor of 4 out in front. So not difficult if you know the trick, difficult if you don't. So that's the end of number 5. Now we're into the last half. We're going to go ahead and start on number 6. All right, so here's integral number 6. We have the integral of 3x over x squared minus 4x plus 4. So the trick here is that we have a polynomial function in the numerator and denominator, which usually will give you a hint that it's either going to be some type of u sub or it might be a partial fraction. In this case, u sub doesn't help us. This one is going to actually have to be partial fractions. So we're going to work with this fraction that we have right here. So we're going to have 3x over, let's go ahead and factor that denominator. Now, you can factor this however you'd like. It actually factors to be x minus 2 squared. Okay, so we want to try to break this into a partial fraction decomposition. So I'm not writing the integral sign down here because I'm just going to change it at the very end. But the trick, the difficult part about this one is most of you will know that you start out with like the a over x minus 2. That's fine. But we need another factor. We need a plus b over, we actually are going to need x minus 2 squared right here to get the correct decomposition. This is a repeated root, which is why we have to do that. So anytime you have a repeated root, you do the individual root, and then you do the entire thing next. If we had a third power, we'd have to do it again. So this is how we're going to have to set up our partial fractions. Now we just need to figure out what a and b are. Because if we can do that, then these just become u sub integrals, and they're not too bad. So the way that I'm going to start this is I'm going to multiply everything by x minus 2 squared. I want to clear those fractions out. So if I do that, I'm going to multiply by x minus 2 squared on both sides of this equality. I'm going to get that 3x is equal to a times x minus 2 plus b. Right? Because the x minus 2 squared will cancel all these out. We just get a b. We'll have 1 that cancels here, which is why we still have the extra factor. And then, of course, both of them will cancel out right here. So then I get that 3x is equal to ax minus 2a plus b. But this is actually really easy to figure out what a and b is because we only have one term that involves x. So we know that 3x has to be equal to ax, which means that a needs to be equal to 3, right? Just because of these two terms right here. So we know that a needs to be equal to 3, but then what does this part have to equal? Well, we don't have any constant term, right? So we know that 2a plus b should actually have to be equal to 0. But if I know what a is, then I know that negative 6 plus b has to equal 0. So, of course, b is equal to 6. Right? So these will work. If I plug in a 3 here and a 6 here, I'm going to get the same thing if I were to simplify those and combine them together. So then I can integrate this now. We'll pull down here. This is going to be a over x minus 2, so 3 over x minus 2. And then we have plus b over x minus 2 squared. So we're going to have 6 over x minus 2 squared. Remember, all of this is still with a dx. And by technicality, we're going to actually pull these integrals apart and work on them separately. So we have the integral of 3 over x minus 2 dx plus the integral of 6 over x minus 2 squared dx. And I'm going to make one big u sub here. So I'm going to say u is x minus 2, which means du is dx. And at this point, we're going to trade these in for a u integral that's much easier to solve. So let's move over here. We're going to have the integral of 3 over u, the integral of 3 over u du, plus the integral of 6 over u squared, which I'm going to write as 6u to the minus 2 du. This one's pretty easy. This is just a natural log. So we have 3 times the natural log of the absolute value of u. And then this one, we're going to have to raise that power up 1, so it'll become negative 1, and then divide by that power. So it's going to actually be a negative 6 over u, and then we'll have a plus c. But again, not technically our final answer because we need to go back to the x world here. So it's going to be 3 times the natural log of the absolute value of x minus 2 minus 6 over x minus 2 plus that constant c. And that will be our answer for number 6. So again, for those of you familiar with partial fractions, may not be too bad at all. It's just that repeated root makes this one a little bit trickier because you have to remember it. And yeah, I think this is a good question for number 6. So now I think is where this really gets tricky. So we're going to go ahead and start on number 7. All right, so here's integral number 7. So we have the integral of 1 over 2 plus e to the x dx. Now this was actually in one of my integration practice videos, and I think it's a very interesting one because you don't often have to bring things into integrals. You usually have like your definite strategies that work out really nicely, but this time we actually need to incorporate a new factor that we add in. So what we're going to do is we're going to realize that this is the same thing as the integral of e to the x over e to the x times 2 plus e to the x. Right, this is exactly the same thing. All I did was multiply the top and the bottom by an e to the x. But that changes nothing. And so now we can actually start with a u sub and then work our way into partial fractions. So if we say that u is equal to e to the x, then we know that du, of course, is e to the x dx. So that covers this part right here, but we still have everything down here that we need to worry about. So when we transfer this to a u sub, we're going to have the integral of 1 over u times u plus 2 du, right? Because our e to the x here gets traded out for a u, and so does this one. And then at this point, again, like I said, it's just going to be partial fractions. It's really not too hard at this point. So we know that 1 over u times u plus 2 should be equal to a over u plus b over u plus 2. Right? And then again, we want to multiply by that least common denominator, which is going to be just everything that's right here. So we'll get that 1 is equal to a times u plus 2 plus b times u. And then, of course, that's going to tell us that 1 is equal to au plus 2a plus bu, which tells us that 1 is equal to a plus b times u plus 2a. So what do we want here? We want a plus b to be equal to 0, right? Because there is no u term over here. And if these are going to be equal, there has to be no u term. And then 2a needs to be equal to 1. So I have that 2a equals 1, which tells me a is equal to 1/2. And then if I know that a plus b needs to equal 0, then I can just say that b is equal to negative 1/2. Because if I add these, of course, I will get 0. So now we can bring this integral down here and replace it for that partial fraction form. So we have the integral, it's going to be a over u, so that's 1 over 2u, right? That's 1/2 times 1 over u. And then we'll go ahead and split the integrals up here as well. We have negative 1/2, so we're going to have minus the integral of 1 over 2 times u plus 2 du. So this was me splitting it up into the partial fractions. I didn't show that step because we did it on the last one. It's exactly the same thing, and we're splitting those integrals up. And then now these would just be pretty simple u subs here. So this one is just going to be 1/2 ln of the absolute value of u, and then we'll have minus 1/2 ln of the absolute value of u plus 2 plus c. And then again, we started out in the x world. We want to end in the x world as well. So we're going to replace these with, so the u's with e to the x's. So this will give us 1/2 ln of the absolute value of e to the x minus 1/2 ln of the absolute value of e to the x plus 2, and then plus a c. Now, we can do one step better because technically we don't need those absolute values. Because e to the x is an exponential function. It's always positive. So we'll never have to worry about a negative input for the natural log. We'll never have to worry about 0 either because exponential functions can never equal 0, as they are without any transformation. So this is 1/2 ln of e to the x minus 1/2 ln of e to the x plus 2 plus c. But ln of e to the x is just going to be x. So we end up with a final answer of x over 2 minus 1/2 ln of e to the x plus 2 plus c. So that is our answer there. So again, the reason that I chose this one to be number 7 is because not only do you have to introduce the factor of e to the x, you also have to switch into partial fractions, and then you even have to do a substitution once you get down here by technicality to get this to be the right answer. So yeah, that's it for question number 7. we'll go ahead and move on to question number 8. All right, so now we're going to start on question number 8. So this is the integral of secant cubed x dx. So this one is tricky, and it's actually very similar to one of the ones I did in my last video. And we'll actually need to use it for 9 and, well, I think 9 and 10. But we're going to set this value equal to I. And you'll see why we do this here in a second, but we need to kind of develop a strategy for this. So this is a trigonometric integral that has a third power on secant. So the usual trick that we try to do is going to be, let's separate this into, a couple of different products. So let's rewrite this as the integral of secant x times secant squared x dx. Right, this is the same thing because secant times secant squared is secant cubed. But now what we can do is we can split this into integration by parts. And the reasoning behind that is because secant squared we can use as our dv, because we know that the integral of secant squared is just tangent. So we set this to be our u, we set all of this to be our dv, and we'll set that up. So we're going to say u is equal to secant x, which means that du is secant x tangent x. And then we're going to say that dv is equal to secant squared x dx, which means that v is equal to just tangent x. So we're going to do our integration by parts formula. So uv is going to be secant x tan x minus the integral of v times du. So that's actually going to be secant x times tangent x, or tangent squared x dx, right? Because we have v du is going to be secant times tangent times tangent. So secant tangent squared, okay? So now what we want to do is, we don't really have like a nice u sub we can do. Integration by parts looks bad at this point in time. So what we're going to do is we're going to rewrite tangent squared as one of the Pythagorean identities. So if you don't remember that, we have the identity that tangent squared of x plus 1 is equal to secant squared of x. So if I want to rewrite that in terms of secants and ones, I know that tangent squared x, so it's right here, tangent squared x is going to be secant squared x minus 1. So let's substitute that in. So we get secant x tan x minus the integral. I'm going to go ahead and FOIL it out, right, because I'm just distributing this with this. And I get secant cubed x minus secant x. And then all of this with the dx right there. Now, it really looks like we've gotten much worse, right? We started out with the integral of secant cubed x, and now we have the integral of secant cubed x minus the integral of secant. Or sorry, just minus secant in the integral. And although that looks, not promising, it actually helps us out a lot, because we're going to split this integral up, right? So this is going to give us, so secant x tan x on the outside stays, but now we're going to have minus the integral of secant cubed x dx. And I'm splitting this up, so this is going to be plus the integral of secant x. So plus the integral of secant x dx. And the benefit of this now is that this right here was our initial I, right? This was our initial integral. And we know that at this point, everything has been equal to I. So if I just add this to the left side, I get that 2 times I is equal to secant x tan x plus the integral of secant x dx. So at this point, we can solve for the value of I if we just divide everything by 2. So we're going to get most of the way there, but we have I is equal to secant x tan x. We'll have plus, I'm going to get rid of this, plus the integral of secant x dx, and all of this is over 2, right? So this is our value, of course, plus c, don't forget that, because it's indefinite. This is a value, but we still need the integral of secant x. Now, you may know this one by heart. You probably know how to do it, but if you don't, we'll go ahead and add that to this. So if we take the integral of secant x dx, what we need is to add in an extra factor. So this was just like the last one where we needed to multiply by a factor in the top and bottom. We need to do the same thing here. What we need to multiply is secant x plus tangent x. So this is the same thing as the integral of secant x times secant x plus tan x over secant x plus tan x, and then the dx. And at this point, we're going to distribute that numerator out. So this gives me the integral of secant squared x plus secant x tan x all over secant x plus tangent x dx. And then we will have to do a u sub. So our u sub is going to be the denominator. So we'll say that u is equal to secant x plus tangent x, which means that du actually ends up being really nice and it turns into the numerator, right? So the du is going to be secant x tan x, I'll have to write it down here, plus the derivative of tangent is secant squared. And then we'll need that dx right here. But again, that is just the numerator and the dx. So when we change this into a u sub, we just have the integral of 1 over u du, which of course is the natural log of the absolute value of u plus c. And then we're going to plug our u back in. So we're going to get natural log, the absolute value, secant x plus tan x plus c. So the reason that I do that is because technically this is not a valid answer yet because we still have an integral in the answer. So we're going to go ahead and rewrite it now, knowing what we have here. So we have that I is equal to secant x tan x plus the natural log of the absolute value, secant x plus tan x, all over 2, and then plus that constant c. So this is our answer for secant cubed x dx. So I put this one so far because you do have to know how to set up this integral in terms of like making it equal to I and then adding things over to both sides. And then we also have to know how to integrate secant, right, if we're not allowed to use that. So this is a pretty tricky integral. It took up the whole board here. But yeah, so that was the end of number 8. We can go ahead and move on to question number 9. All right, so we're getting close to the end now. Here is integral number 9. So we have the indefinite integral from negative infinity to infinity of e to the minus x squared dx. Now, this is a very non-elementary integral. We need to use polar coordinates. We also need to convert it into, a double integral, of course, to use polar coordinates. And it's just very tricky all around. So there's a lot of tricks here, which is why I put it at number 9. So we're going to use the same kind of idea, and we're going to set this equal to I. Now, we want to try to get this into a form where we can use polar coordinates and make it a double integral. And the way we have to do that is we actually need to consider I squared. So I'm going to write down what I squared is, and then I'm going to justify why that's actually the square. So I squared, we're going to write as the double integral, both of these from negative infinity to infinity, of e to the negative x squared minus y squared dx dy. Okay, so it may not be immediately obvious why this is the square, but I want to justify that to you. So we'll kind of do an aside for that. Let's look at the inside integral here. We know we can rewrite everything in there as, let's write everything out, I guess. Negative infinity to infinity. We can rewrite what's on the inside as a product of e to the exponential terms, right? So we have e to the negative x squared times e to the negative y squared. Right? This is exactly the definition. Of course, we still have dx dy, but exactly the definition of our exponential multiplication. But now we need to look at this e to the negative y squared term, right? This is actually a constant in this first integral, right? This is our first integral with a dx. This term right here is a constant. So we can actually rewrite this as the integral of negative infinity to infinity. We can pull this out, e to the negative y squared, and then we have our inside integral of e to the minus x squared. We still have dx dy out here. But now let's look at our inside integral. Our inside integral is what we just said was I, right? So what we have now is the integral from negative infinity to infinity of e to the minus y squared times I dy. And since I is a definite integral, we know that we can get a number for it, right? It has some numerical value, which means we can factor it out of the integral. So I get I times the integral from negative infinity to infinity of e to the minus y squared dy. But if for this to be equal to I squared, we know that this integral has to also be equal to I squared, or sorry, equal to I, because I times I would give me I squared. And it does reasonably make sense that that would be equal to I because nothing is changing. We just changed what variable we're using, right? I'm still integrating from negative infinity to infinity. The input is still e to the minus y squared rather than e to the minus x squared. They're the exact same thing. So these integrals will result in the same value, which means that this is equal to I squared, right? So this is kind of our justification that what we did here was equal to I squared. Now we can evaluate that. And the beautiful thing about this is that we can directly use polar coordinates for this, right? Because I know that this is still equal to, let's separate this. This is equal to the double integral, so negative infinity to infinity, same thing here, of e to the minus x squared plus y squared, right here, dx dy. And now we know that x squared plus y squared is equal to r squared when we convert to polar coordinates. And we know that dx dy translates to r dr d theta. So the only other thing we need to figure out is what the bounds do. So I'm going to write convert to polar. So convert to polar coordinates. We just want to look at our bounds. So what I'm going to do is I'm going to use the radius on the outside integral and the theta on the inside integral. So if we're integrating from negative infinity to infinity on both x and y, that means we're really integrating the entire coordinate system. And for that to be the case, we have to also do the same thing for polar. So we need our theta to go from 0 to 2 pi, right? Because that's going to be the entire, every possible value for theta is in between 0 and 2 pi on the unit circle. And then our radius, well, it's going to be from 0, the smallest possible radius, to infinity, right? Because it can be as big of a radius as we want since it's the entire coordinate system. And then now we know that this translates to r e to the minus r squared, and this will be d theta dr. Right, so this was just a conversion to polar coordinates because we know this is r right here. We know that we need r dr d theta for this. So d theta dr is the same thing by Fubini's theorem. And then now we can integrate this. And it's actually much, much easier at this point. Because when we do this first integral, we're integrating with respect to theta, but there's no theta in here. So everything we have here is a constant, which means we just add a factor of theta. So it's the integral from 0 to infinity of theta times r e to the minus r squared, evaluated from 0 to 2 pi, and then we have this dr out here. But the only thing that adds is an extra factor of 2 pi, right? Because when I plug this in here, I get the 2 pi, and then the 0 will make everything 0. So what I have is the integral from 0 to infinity of 2 pi r e to the minus r squared dr. And then at this point, all we need is a u sub. So we'll say that u is equal to negative r squared, which means du is minus 2r dr. Right, so then what we're going to have here when we convert is, I'm going to go ahead and just pull the pi out in front for reference. We'll have pi times the integral, and we'll worry about the bounds at the end. The 2r is completely gone. We have a negative in here, and then we have the negative e to the u. Right, this was our u that we used. Everything else goes away. We pulled the pi out. The 2r goes with the dr, and then we have that extra factor of negative 1. So then when we evaluate this integral, we get negative pi e to the u. And again, we want to go ahead and try to put that back into that r form that we had. So this is going to give me negative pi e to the minus r squared. And we're evaluating this from our original bounds 0 to infinity. All right. So now when we just plug in what we have here, again, this is where it's technically improper, so you'd want to really use a limit, but we'll skip that part for now. It shouldn't change anything. When we plug in infinity for the first one, it's going to make this exponential term very large and in the denominator. So we go to 0, And then we have minus, so we'll have a negative pi, and then we'll have e to the 0. E to the 0 is just 1, so it's just 0 minus negative pi, and that is going to give me a positive pi. So very interesting. We got pi from this integral. I mean, it intuitively makes sense. We're in polar coordinates. We're kind of using these thetas that have pi's in them. But we didn't start in polar coordinates. We started up here, and we also started with just one copy of I. So if you boxed pi here, you would actually be incorrect because this is I squared, right? This was equal to I squared. So if we want I, we just need to take the square root of it. So we know that I, which is this integral right here, so let me write that, the integral from negative infinity to infinity of e to the minus x squared dx is equal to the square root of pi. And that is our answer. So very tricky there, because you have to set this up in a way where we can use these polar coordinates. But even that is tricky because we have to go through and prove that what we tried to do does actually give us what we wanted to. And then, doing the polar integral shouldn't be too hard for the Calc 3 students or further on. But yeah, this is a very interesting question. Square root of pi is an interesting answer. And this is an integral that if you study probability theory, this will come up all the time. It's very important in probability theory. But that's outside of the scope of this video. We're going to go ahead and move on to the final question of this video. So this is integral number 10. Good luck on it for those of you trying it. All right, so here we have question number 10, the final question of this video. So hopefully you all were happy with this. This is a pretty tricky ending question, but I think that I still kept the video manageable for your average calculus student. So hopefully you all have enjoyed, and we'll go ahead and start with question 10 here. So we have the integral from 0 to infinity of sine x over x. This is a very tricky integral because the elementary techniques that we have won't work. We actually will need to use Feynman's trick, which isn't taught very often, I find, in calculus classes, but it can be very useful. So Feynman's trick basically says we want to set up a function of a different parameter. So in this case, let's set up a function of s. So we'll say that f of s is going to be equal to the integral from 0 to infinity. And here's how we're going to set it up. We're going to have e to the minus sx times sine x over x. Now, some of you who may have taken differential equations will recognize this as the Laplace transform. And that's exactly how we're going to solve this. We're going to try to evaluate this integral, and we have to use Feynman's technique. And so the way we set this up here is we want to take the derivative of this, because what this is going to do, if we can take the partial derivative with respect to s, we're going to be able to cancel out this x that's in the denominator. And that will help us because if you think about it, that's the only thing that's restricting us from being able to solve this. Right? If we didn't have that factor of x in the bottom, it would be a very easy integral. So we want to eventually try to get rid of that. And that's what setting it up like this is going to do. So let's take the derivative of our function here. So f prime of s, again, we need the partial derivative because we have s's and x's. But we're going to take the partial derivative with respect to s of this function that we have on the inside. So e to the minus sx times sine x over x dx. So when we take that partial derivative, all the x terms are constant. So we're just going to get the integral from 0 to infinity of, we're going to have a negative x term that gets pulled down. We'll have e to the minus sx times sine x over x dx. But you can see how beneficial this is because now we can cancel out that denominator like we said because we have this being multiplied by it. So those x's cancel and we get the integral from 0 to infinity of negative e to the minus sx times sine x dx. And again, I want to emphasize that this is f prime of s. So again, we want to set up this function because we can make this a much easier thing to integrate because at this point in time, we just have a integration by parts. That's all we really have. So we want to set that up. So we're going to say that this is going to be our u, and this is going to be our dv. So we know that u is equal to negative e to the minus sx, which means that du is going to be se to the minus sx dx. we know that dv is going to end up being sine x dx, which means that v is going to be negative cosine x. And so now we can go ahead and do our integration by parts formula. So uv is just going to be e to the minus sx cosine x, evaluated from 0 to infinity because we pulled that part out. And then minus v du will actually turn into a plus the integral from 0 to infinity. We'll have se to the minus sx times cosine x. And so we can evaluate this one because when we plug in infinity, we're going to get 0 for the first term because we have that negative exponential. And we're going to subtract off, if we plug in 0, we're going to get 1 times 1. And so we're subtracting off 1, so we get negative 1. And then plus, well, now we have a new integration by parts integral. So we have the integral from 0 to infinity of se to the minus sx times cosine x dx. But we actually have to use integration by parts again on this. So we're going to do the same idea. This is going to be u, this will be dv. So if u is equal to se to the minus sx, then that means du is going to be negative s squared e to the minus sx dx. And then dv is just cosine x dx. So this is nice and refreshing. This is just going to be sine x. So then we need to set up our integration by parts again. So we still have the negative 1 that's out here. So we have negative 1 plus. Now we have a new uv. So this one is going to be se to the minus sx times sine x, again evaluated from 0 to infinity. And then since v du is negative, we can make it a plus. The integral from 0 to infinity of, we'll have s squared e to the minus sx times sine x dx. And then again, we can evaluate this part right here. So if we plug in infinity, we get a very small exponential down there. It will actually end up giving us, it'll be 0. It'll be 0 because sine x, it can only fluctuate between 0 and 1, but this will continue to grow. So it will be 0 there. And if I plug in 0, sine of 0 is 0. Right, so this entire term goes away and becomes 0. Then we just have this right here. So we end up with negative 1 plus, and then here's what I'll do. We can pull s squared out of this integral, right? There's no issue with that because it doesn't have any relation to x, right? So we can pull s squared out. So we get s squared times the integral 0 to infinity of e to the minus sx times sine x dx. So at this point, we've done integration by parts twice. And it doesn't look like it's really helped us, but if you look back at our original f prime, we're very close. The only thing we're off by is this factor of negative 1. So we know that this right here is equal to negative f prime of s. So what we found is, because we were integrating f prime of s the entire time, so we found that f prime of s is equal to negative 1 plus, it won't be a plus because it will be the negative version of f prime. So minus s squared times f prime of s. So this is just like what we did in the secant cubed integral, and even a little bit like what we did in the last one, where we've got the same integral as the solution to an integral. So all we need to do is add this term over here, and what we end up getting is that f prime of s times 1 plus s squared is equal to negative 1. Right, I'm factoring f prime of s out of there. And so to solve for f prime, I'm going to get that f prime of s is equal to negative 1 over 1 plus s squared. Right, so this is actually very nice because we've got something that doesn't have anything to do with an integral for our solution for f prime of s. And so that's super nice. Now, the reason that we set up the function in the first place was because if we were able to plug in 0 to this function, we would get the value of our integral, right? Because if I plug in 0 for s, this is just 1. So it's just the integral from 0 to infinity of sine x over x, and that's what we're looking for. So if we know that f prime of s is equal to negative 1 over 1 plus s squared, to get back to f of s, we just want to take the integral of that. But the beautiful part about this is that the integral here is not that hard. It's just an arctan. So we know that f of s is going to be equal to negative arctan of s plus some constant c. So we know we have good intuition on what arctan of s is going to be, and we want to plug 0 into this. The problem is we don't know what c is. So we need to examine this just a little bit further to figure out what our c needs to be so that we can actually plug in 0 and get our solution for the integral. So the way we're going to do that is we're just going to compare the limits of both of these as they go to infinity, right? Our integral goes from 0 to infinity. So we'll compare the infinite limits. So we know that the limit as s goes to infinity of f of s can be written in two different ways. It can be written as the limit as s goes to infinity of the original integral, right? So the integral 0 to infinity of e to the minus sx times sine x over x dx. Or it can be rewritten as this limit. So the limit as s goes to infinity of negative arctan of s plus c. Right, so we want to try to figure out which one of these we can actually solve. And the only one that we could get the limit value to would be this integral one, because this one we don't know what c is. So we have no idea what the limit as s goes to infinity would be, because c would be a vertical shift. So let's look at this integral down here. What can we tell? We can say that as s goes to infinity, right, we're going to have, this is going to come down into the denominator with this right here, and it's going to grow extremely fast. We have sine x that is in the numerator, right, and that is not going, it's not going to grow very fast, and it never grows past 1 for that matter. So we know that the denominator is growing super fast, which means that the inside of the integral is going to 0. But if we integrate 0, of course, there's going to be no area underneath that. So this limit we can actually evaluate to be 0 as s goes to infinity. So we need this limit to be 0. But we know that the limit as s goes to infinity of negative arctan, well, if we look at the arctan graph, so let's put this right here. The graph of arctan, it's a little funky, but it ends up looking something like this, and it has this horizontal asymptote here at pi over 2. So we know that if we look at negative arctan, we're going to have, this negative pi over 2 right here as well, which means that as s goes to infinity, we have negative pi over 2 plus c. But we want to figure out what c is, and we know that the limit should be 0, which means that c would also have to be pi over 2, right? For this to be 0, c has to be equal to positive pi over 2. So then what that tells us, and I've got to go all the way down here, we have that f of s is equal to negative arctan of s. I'm going to erase this, I'll put this right here. Negative arctan of s plus that c, which we just found out was pi over 2. And again, the intuition behind making this function in the first place was so that we could plug 0 in at the very end and get a numerical value. And if you notice, we plug 0 in for s, right? It's going to give us our original integral, but we can plug it into this much nicer form, and arctan of 0 is 0, right? So we have f of 0 is 0 plus pi over 2. So that means that this integral right here is equal to pi over 2. So a very nice solution to a very ugly integral, right? We had to use Feynman's technique. We had to take the integral of the derivative of the function that we set up. It's very, very difficult here. We end up getting to this much nicer form after just doing integration by parts twice. We end up with negative arctan s plus c, but we don't know what c is, right? Because this right here is a family of functions, and we need to figure out the exact one. But we're going to infinity, so if we get that value of c by looking at these limits, then we can immediately plug in 0 and get a numerical value. So, very difficult question, sure. Hopefully some of y'all were able to get it. If you have any questions about this, please let me know. But I hope you enjoyed this video. I appreciate you watching it, and I hope this was good. I do plan on doing a part 3 because these are just way too fun to make. But yeah, so I hope you enjoyed. If you have any questions, again, let me know. If you have any comments, any complaints, let me know that as well. But if not, then I will see you in the next video. Thanks for watching.